all present here in my presentation. Today I'm going to present my topic on optics. So now let us go through the contents of the topic, which are optics, history of optics, lenses, lens terminology, uses of lenses in daily life, slide projector, photograph enlarger, classical optics, approximations, reflections, refractions, diffraction and optical resolution, dispersion and scattering, and the last polarization. So, what is optics? Optics is the branch of physics that studies the behavior and properties of light, including its interactions with matter and the construction of instruments that use or detect it. Optics usually describes the behavior of visible, ultraviolet, and infrared light. Since light is an electromagnetic wave, other forms of electromagnetic radiation, such as X rays, microwaves, and radio waves, exhibit similar properties. So, now let us go through the history of optics. So, optics began with the development of lenses by the ancient Egyptians and Mesopotamians. The earliest known record for lenses made from polished crystal, often quartz, date from as early as 2000 BC from Crete. It is an archaeological museum of Heraklion, Greece. Greek philosophy on optics broke down into two opposing theories on how vision worked: the intromission theory and the emission theory. Plato first articulated the emission theory, the idea that visual perception is accomplished by rays emitted by the eyes. Basically, the vision theory states that light is emitted from our eyes through which we can see the objects around us. During the Middle Ages, Greek ideas about optics were resurrected and extended by writers in the Muslim world. One of the earliest of this was Al-Kindi, c. 801 to 873 time period, who wrote on the merits of Aristotelian and Euclidean ideas of optics, favoring the emission theory since it could better quantify optical phenomena. In 13th century in medieval Europe, English bishop Robert Grosseteste wrote on a wide range of scientific topics and discussed light from four different perspectives. Firstly, an epistemology of light. Second, a metaphysics or cosmogony of light. Third, an etiology or physics of light. And fourth, and the last, theology of light, basing it on the works Aristotle and Platonism. And then you can see the first wearable glasses were invented in Italy around 1286 AD. This was the start of the optical industry of grinding and polishing lenses for these spectacles. First in Venice and Florence in the 13th century, and later in the spectacle making centers in both the Netherlands and Germany. Spectacle makers created makers created improved types of lenses for the correction of vision, based more on empirical knowledge gained from observing the effects of the lenses rather than using the rudimentary optical theory of the day, basically today, theory which for the most part could not even adequately explain how spectacles worked. This practical development, mastery, and experimentation lenses led directly to the invention of the compound optical microscope around 1595 and the refracting telescope in 1608, both of which appeared in the spectacle making centers in the Netherlands. In the 17th century, we can see that Johannes Kepler expanded on geometric optics in his writings, covering lenses, reflection by flat and curved mirrors, the principles of pinhole cameras, inverse square law governing the intensity of light, and the optical explanations of astronomical phenomena such as lunar and solar eclipses and astronomical parallax. He was also able to correctly deduce the role of the retina as the actual organ that recorded images, finally being able to scientifically quantify the effects of different types of lenses that spectacle makers had been observing over the previous 300 years. After the invention of the telescope, Kepler set out the theoretical basis on how they worked and described an improved version known as the Keplerian telescope, using two convex lenses to produce higher magnification. Then we can see that Newtonian optics was generally accepted until the 19th century, when Thomas Young and Augustin Jean Fresnel conducted experiments on the interference of light that firmly established light's wave nature. Young's famous double experiment showed the light followed the superposition principle, which is a wave-like property not predicted by Newton's corpuscle theory. This work led to a theory of diffraction for light and opened an entire area of study in physical optics. Wave optics was successfully unified with electromagnetic theory with James Clerk Maxwell in the 1860s. The next development in optical theory came in 1899 when Max Planck correctly modeled black body radiation by assuming that the exchange of energy between light and matter only occurred in discrete amounts, which he called as quanta. In 1905, Albert Einstein published theory of the photoelectric effect that firmly established the quantization of light itself. Basically, photoelectric effect means the light rays, as in photons, when they hit a metal surface, electrons ejected from that metal surface. Now let us see what are lenses. Lenses are an important part of optics through which we can know deeper about the world by using light. Lenses are the pieces of transparent material of which one or both sides are spherical. It is any transparent material having two surfaces of which at least one is curved. Lenses refract light in such a way that an image of the object is formed. Each surface of a lens is a part of a sphere. Common types of lenses are the convex lenses, concave lenses, and contact lenses. But here we are going to discuss only on the two types, convex and concave. So, types of lenses in physics. Firstly, convex lenses, the lenses which causes incident parallel rays to diverge at a point is known as convex or converging lenses. This lens is thick at the center but thin at the edges. And concave lenses, another type of lens, causes the parallel rays of light to diverge from a point. This is called concave or diverging lens. The lens is thin at the center and thick at the edges. As we can see in the following images of converging lenses and diverging lenses, the three different types for each type of lenses. Like for converging lenses or convex lenses, we can see the double convex, which has both sides convex, planar convex, which has one side convex, one side plane, concavo convex, which has one side convex, one side concave. And for diverging lenses we can see the double concave, which has both sides concave and the middle is thick, and the planar concave, which is one side plane and one side concave. The convexo concave, which we can see as one side as concave and the other side is convex. Now let us go through the terminology of lens, basically the lens terminology. The first thing to go through is the principal axis. What is the principal axis? Basically, each of the two surfaces of the spherical lens is a section of sphere. The line passing through the two centers of curvature of the lens is called the principal axis. Like here we can see in this lens, this line passing through the optical center O is basically the principal axis. And what is the optical center? Optical center is the point of the principal axis, the center of the lens, and this particular point is called the optical center. And the principal focus, basically this here, this is the light travels parallel. Basically, we can see the lights are traveling parallel here. So when the light travels parallel to the principal axis of a convex lens, and after the reflection, the rays meet at a point on the principal axis called the principal focus of focal length, a focal point of, or f. It's basically f. Hence the convex lens is also called converging lens, and for concave lens it is called the principal focus, not the principal focal point. Hence concave lens is also called diverging lens. What is the focal length? Focal length basically the distance between the optical center and the principal focus. The power of a lens is defined as the reciprocal of the focal length in meters. So basically the focal length, basically it is power P equal to 1 by F, and the unit is diopter, D, capital D. Now let us try to see the image location by the lens equation. Basically, let us consider an object here. Let it be considered as OP. This is placed in front of this convex lens at a distance P, a ray PR. Basically, you can take like this. Let this be PR. A ray PR parallel to the principal axis of reflection passes through the principal focus, here F. Focus. Another ray PC meets the first ray at point P. Passing through the optical center. Basically you can consider this ray to pass through the optical center, and this one is like it's going here and it's a reflector and it's touching a point and it's forming an image O dash P dash. Basically this is inverted, therefore it is a real image, and so then you can see the size and this all things. Therefore we can define the lens formula as the relation between the object and the lens formula as the relation between the object and the image distance from the lens in terms of the focal length of the lens, and it's called the lens formula. Basically it's like the relation between the object and image distance from the lens in terms of the focal length of the lens, and this is called the lens formula. Basically now if we are moving on to the sign conventions for lenses. Here we can see magnification. What's magnification? Magnification is the ratio of the size of the image to the size of the object, and this is called magnification. When an object is placed in front of a convex lens at a point beyond its focus, a real and inverted image of the object is found. This is actually so then what is the magnifying power? The magnifying power can also be stated as the angular momentum. No, sorry, not momentum. Angular magnification, and this is defined as the ratio of the angle subtended by the image as seen through the optical device to that subtended by the object at the unaided eye. And the optical resolution of a microscope or telescope tells us how close together the two point source of light can be so that they are still seen as two separate sources. Actually, this can be seen using a microscope, telescope, and stars and small things, microscopic things. Basically, now let us see what is resolving power. Basically, the resolving power of an instrument is its ability to reveal the minor details of the object under examination. So basically, resolving power is expressed as the reciprocal of minimum angle which two point sources subtend at the instrument so that their images are seen as two distinct spots of light rather than one. And then you can see that and then you can see the derivation here. It's like the result power r equal to 1 by lambda minimum, not lambda, sorry, it is basically alpha minimum, and equal to d by 1.22 lambda. Basically, lambda is the wavelength, d is the diameter of the lens, and then you can see where alpha minimum equal to 1.22 lambda by d, and you can see it as resonant power is equal to lambda by lambda 2 minus lambda 1 equal to lambda by small change in the lambda, or a very small, we can consider it as a very small part of lambda. Basically, if we consider n is the number of what you call rulings on the granting, or basically if you consider m as the number of order and n as the number of rulings on the grating, we can show the resultant power as r equal to n into m. Now let us move forward to the uses of lenses in daily life. The application of lenses in some optical devices such as cameras, light projector, and photograph enlarger. Basically, we can and then many more things like the magnifying glass, the microscope, the spy hole in a door through which we can see outside, the flashlight, the headlights, the indicator lights of a car, many things, traffic signals, etc. So basically, what is accommodation? Basically, lens, camera, and human eye. Basically, the human eye also works like a camera, right? We know that, and so basically accommodation is nothing but the variation of the focal length of an eye lens to form a sharp image on the retina, and this is called accommodation. Basically, it means that like our eyes has a lens, means it is the shape of lens. So in that, the variation of the focal length of the eyes lens uh, to um, to form a sharp image on the retina is called accommodation. Basically, when the focal length of the eyes lens varies uh, uh, to form a sharp image on the retina, this is called accommodation. Like the best example is this focusing on this camera. Like here, when we focus, we have to like the variation of the focal length happens, and then we see a sharp image on the retina, basically a clear image on the camera screen and all. So basically, you can see that the camera focuses on a object at a distance. The same thing happens for a slide projector and photograph enlarger. It focuses on a particular screen and photograph, and it's like enlarging or reducing the screen size based on the requirements. What is classical optics? You can see classical optics defined into two main branches, basically geometrical or ray optics and physical or wave optics. What is geometrical optics? Geometrical optics or ray optics describes the propagation of light in terms of rays, which travel in straight lines whose paths are governed by the laws of reflection and diffraction at interfaces between different media. These laws were discovered empirically as far back as 984 AD and have been used in the design of optical components and instruments from then until the present day. They can be summarized as follows. When a ray of light hits the boundary between two transparent materials, it is divided into a reflected ray and a refracted ray. For example, we can take a piece of glass. One side we can consider the medium to be as water and other side to be air or vacuum. And so when the ray strikes the glass, one part of the ray gets reflected and the other parts gets refracted through the medium of water. The law of reflection says that the reflected ray lies in the plane of incidence and the angle of reflection equals the angle of incidence. Approximations. Geometrical approximations is often simplified by making the paraaxial approximations or small angle approximations. Basically, it's like the geometrical what you call optics is simplified by making small angle approximations. Similarly, you can the mathematical behavior then becomes linear when you do that, and it allowing the optical component system to be described by simple matrices. So basically, the material when we take small angle approximations for geometrical optics, the mathematical behavior becomes linear, and therefore we can then for optical components and systems you can describe them by using simple matrices itself. This leads to the techniques of Gaussian optics and parallax ray tracing, which are used to find basic properties of optical systems such as approximate image and object positions and magnifications. So like here we can see the previous year I had seen that this incident ray hits it, it's reflected, it gets refracted. This is the refractive index of water or any other medium. This is the vacuum, and this is the interface, and this is the angles created on both sides. So what is reflection? So reflection can basically reflection happens when this incident ray strikes the plane and the ray is what do you call basically it strikes the plane at the normal and it gets basically it goes in another direction in the very same medium at a particular angle. In the very same angle it strikes most of the times. So reflections can be divided into two types: specular reflection and diffuse reflection. Basically, specular reflection describes the gloss of surface such as mirrors, which reflect light in a simple, predictable way. This allows for the production of reflected images that can be associated with an real or virtual location in space. And diffuse reflection describes non-glossy materials such as paper or rock. The reflections from these surfaces can only be described statistically with the exact distribution of the reflected light. Depending on the microscopic structures of the material, many diffuse reflectors are described or can be approximated by Lambert's Gaussian law. This law basically states or describes that surfaces that have equal luminance when from any angle. Basically, it describes the surfaces that have equal luminance from any angle. And glossy surfaces can give both specular and diffuse reflections. So this diagram of specular reflection, you can see here. It is like this and And then refraction. Refraction occurs when the light travels through an area of space that has a changing index of reflection. Changing index of refraction. This principle allows for lenses and the focusing of light. The simplest case of refraction occurs when there is an interface between a uniform medium with index of refraction and the medium with index of refraction. Basically, the refractive index are different. In such a situation, the Snell's law describes the resulting deflection of light ray, which you can see in the equation n1 sine theta 1 equal to n2 sine theta 2. Basically, the n1 is the refractive index of the first medium, n2 is the refractive index of the second medium. Sine theta 1 is the angle formed by the incident ray with the normal in the first medium, and theta 2 is the angle formed by the diffracted ray in the second medium with the normal. And here you can see that the angles between normal and the face and the index of the refraction of medium is related to the speed v of light in that medium by n equal to c by v, where v is the velocity of the light in the medium. So the speed of light in vacuum by v is velocity in the medium in which it's getting refracted. C is the speed of light in vacuum. And so now let us go to the next topic, diffraction. Diffraction and optical resolution. Diffraction basically is the process of which light interface is most commonly observed. Basically, the effect was first described in 1665 by Francisco Maria Grimaldi, who also coined the term from Latin differingere, to break into pieces. And later that very same century, Robert Hooke and Isaac Newton also described phenomena known to be diffraction in Newton's rings, which James George Gregory recorded his observations of diffraction patterns on bird feathers. The first physical model of diffraction that relied on the Huygens Fresnel principle was developed in 1803 by Thomas Young as interface. Basically, experiments with the interface pattern of two closely spaced slits, basically like this slits. Young showed that his results could only be explained if the two slits acted as two unique sources of waves other than corpuscles. 1815 to 1818, Augustin Jean Francois formally established the mathematics of how wave interface can account for diffraction. And then we can see that the simplest physical models of diffraction use equations that describe the angular separation of light and dark fringes due to light of a particular wavelength lambda. In general, the equation takes the form m lambda equal to ds d, with separation between two waves front source. The case of Young's experiments, Young's double cell experiment, is the angular separation between the central fringe and the outer fringe. Central fringe and the outer fringe with the central maxima is equal to 0. Using the equation is modified to take into variety of situations such as diffraction through a single gap, diffraction through multiple cells, etc. And you can see in the diffractions occurring distance d in the bright fringe occurs in lines where black lines intersect with black lines and the white lines intersect with the white lines, and this fringe is separated by angle theta and are numbered as order. Dispersion and scattering. Basically, what is scattering of light? Scattering of light is a phenomenon in which light rays deviate from the original path when striking an obstacle like dust, gas, molecules, or water vapors. Scattering of light gives rise to many spectacular phenomena such as Tyndall effect and red hues that can be seen in sunrise and sunset. The limit of this visual Tyndall effect being a commonly observed result, and a small proportion of light scattered from atom chemicals may undergo Raman scattering when the frequency changes due to excitation of the atoms and molecules, and Brillouin scattering occurs when the frequency of light changes due to local changes with time and movements of a dense material. And dispersion occurs when different frequencies of light have different phase velocities due either to metal properties, or metal dispersion also you can say, or to geometry of an optical waveguide or waveguide dispersion. The most familiar form of dispersion is a decrease in index of refraction with increasing wavelength, which is seen in most transparent materials. This is called the normal dispersion, and basically it occurs in all the electric materials in wavelength ranges where the material does not absorb the light. Basically, it's not absorb light. In wavelength ranges where a medium has significant absorption, the index of refraction can increase with wavelength. This is called anomalous dispersion. Basically, what's anomalous dispersion? It is that when a medium has a significant in wavelength ranges where a medium has significant absorption, the index of refraction can increase with the wavelength. This is called anomalous dispersion. This is a diagram of spectral dispersion. So basically a graph. Wavelength and this one. Now we have come to the last topic of the presentation, which is polarization. What is polarization? Polarization is a general property of waves that describes the orientation of their oscillations. For transverse waves, such as many electromagnetic waves, it describes the orientation of the oscillations in the plane perpendicular to the wave's direction of travel. The oscillations may be oriented in a single direction, basically called linear polarization, or the oscillation direction will rotate as the wave travels, which is called circular or elliptical polarization. Circular polarization, waves can rotate rightward or leftward in the direction of travel, and which of those two rotations is present in a wave is called the wave's chirality. So here you can see linear polarization. Here the waves is going like in a normal way upwards, means not exact normal but still it's like moving here in right to left side and going upwards, and circular way it's like moving in a circle and going up. For elliptical also it's same, that it's moving circular and going up. So thank you for everyone for watching my presentation.